In the previous video in this series I demonstrated this circuit, and this is the start of a design for a switch mode power supply for our Z80 computer project. Now this is the basic design we're going to be using for our switch mode supply, and I said it was fairly simple, and in theory at least the design of a switch mode supply is fairly straightforward. However, in practice they do get incredibly complicated very quickly, and I've seen no end of discussions on forums and online about people having issues trying to design supplies like this. The switching device or the transformer was overheating, that sort of thing, and they were getting no end of failures, and the main reasons are fairly obvious when you look at the schematic or the cores they were using for their transformer, or the general topology they were trying to use was maybe not appropriate for what they were doing. Now there are many different designs for switch mode supplies, but they all really follow one of two basic design philosophies, although the layout and the schematic and the transformer design can all be very different. So the first thing we have to do before we start our design is decide which of the two general topologies we want to select from, and then start to design down the appropriate path to make sure we select the right transformer core, that sort of thing. Now before we go any further, I should point out that a lot of engineers will no doubt complain about the way I intend to go about describing the design process, because what I'm going to do really out of necessity is generalize a lot of the design elements just to keep the videos moving forward. Now if you are interested in much more in-depth discussion about switch mode supplies, then please leave a comment and I will post an entirely separate video series on a detailed design of switch mode power supplies. Now also bear in mind with this particular project that my intention is to design a supply that would have been familiar back in the day when Z80s were in common use, and that's the type of supply we're going to design here. So we'll be using a fairly old type core, and the design will be, as I say, something that will be familiar to anyone designing systems back then. But the general principles are the same. The only thing that's really changed, the materials, core designs, that sort of thing, and also of course switching transistors and MOSFETs are now much better than they used to be back then. So the first thing we do, as I say, is look at the general topology we want to use. This part of the circuit is not really going to change that much for the different topologies, so what we'll do is just sketch out the two general types that we can select from. So they both start with the same elements. We have the transformer, so we have a core, we have a primary winding. The primary winding is switched with a power device. I'll just show that as connected to ground for now, and then we supply it with a DC voltage, and we apply a drive signal to this switching device to turn the primary winding on and off. We then have a secondary winding, and we will rectify the output from that winding, and we will then smooth the output from that, and that will be the output of our power supply. There's generally some feedback from this point back through to the control, but we can ignore that for now. What we're looking at here is the way energy is transferred through the core. So this is a flyback system. So the way this works in general is that the switching device switches on, the current in the primary winding will start to increase. Remember, what we're designing here really, as far as the primary side is concerned, is just an inductor. We can almost forget it's a transformer, but what we're designing is an inductor, and because it's an inductor, when we turn this device on, even though there's usually a supply voltage of several hundred volts, just a few turns on the primary, low impedance down to ground. So even though there's a kind of a low resistance path here, the instantaneous current when we first turn the transistor on is fairly low, and it starts to ramp up as it would with any inductor. What happens from that point on depends to a large degree on the type of core that we use. But in a flyback system, what we do is we turn the transistor on, we allow a flux to build up in the core, so the core stores energy, and then when the driver device turns off, the flux in the core starts to collapse. That induces a voltage or current in the secondary, and thus where energy is transferred to our output. Now, for this to work, we want fairly low direct coupling between the two windings. We don't want the current in the output to really be driven when the current in the primary is ramping up. Might sound a bit counterintuitive for a transformer, but that's not the way a flyback system works. And if we look at the drive to it, if we look at this point, for example, we look at the voltage there, it's going to be doing something like this. This is vastly oversimplified, but this will hopefully give the general idea. So we have the voltage here. When the device turns on, the voltage drops. When the device turns off, the voltage goes back up again. If we now look at the current flowing through the primary, when the transistor turns on, the current will start to ramp up as it would in any inductor, and then when the transistor turns off, the current drops, and then it will do the same thing again when it turns back on, so it will start to ramp up and then it will go back down again. So that's what the current in the primary is doing. The current in the secondary, however, will be doing something more like this. So when the flux in the core, the stored energy, starts to collapse, that will induce a voltage going the other way. That will then subside, and then it will repeat each time the device turns off. So we'll get a current like that flowing in the secondary, and it's this current that we rectify, smooth, and feed to our output. So the important thing to note here is that the energy transferred through the transformer is done by storing energy in the core, not by direct coupling between the primary and the secondary windings. So that's the general flyback topology. Now the other variation we could select from looks very similar initially. So we have once again a transformer for the core, we have a primary winding, and once again this is controlled through some sort of switching device. We supply a drive signal to that device, and once again we have a voltage source. So it looks very similar so far. We have a secondary. Now this is where things start to change. We again rectify the output so that essentially it's only going to conduct, we only get a current loop in one direction through the secondary. But this time, rather than having a capacitor directly here, what we do is we have another inductor, usually a relatively large inductor, and then it's the output of this that we smooth. Okay, and this is generally referred to as a forward converter, and as you can see it looks fairly similar to the flyback, but it works in a different way, in that when the driver device turns on, we want direct coupling between the primary and the secondary. We don't want the core to store any energy, so it works a bit more like a traditional transformer, and then the inductor here is used to store energy. So it works in a little bit of a similar way, but fundamentally the transformer operates in a different mode. Now if you look superficially at some of the schematics around for switch mode supplies, it might be a bit confusing, because you might see a supply that looks more like this. So that you might find you've got a capacitor here, and then you have maybe an inductor, a capacitor there. So it looks like it's a different type of switch mode supply. It looks more like a forward converter because you've got an inductor here. But don't be fooled, this is still in this mode a flyback converter, and this is just here for part of the filtering of the output. Really what you're looking at here is the general direction of the winding. So this is the start of the winding, then the start of the winding on the output will be up here, and for a forward converter this is the start of the winding, then the start of the winding will be down here. So it's an easy way to tell as long as the schematics have been drawn correctly. But just make sure you understand that generally if you have a large capacitor after the rectifier diode, it's more likely to be a flyback, and if you have an inductor after the rectifier, then it's more likely to be a forward converter. So and again, if we draw the difference here, then we'll get switching in the same way for our switching device. But this time, well, the current will be the same, so it will still be doing this in the primary. So it'll look the same at that point. But what's different is that in the output, in the secondary, we'll be getting something that looks a bit more like this. So they'll kind of match because it's directly coupled to the primary. But bear in mind, you'll get a different current flowing through here. Now we're going to select the flyback type of transformer. Now that means we need to select a suitable core. As I said, we want to store energy in the core, but also we don't want the primary and the secondary to be directly coupled. So to achieve this, we use what's called a gapped core. So if we look at a core in cross section, then normally they're shaped something like this. And there's normally two of these on each core, so there'd be another one. I'm exaggerating this here, but what you can hopefully see is that there is a gap between the center pole. So if I show you an example of this type of core, this is a 42 EE style core, and you can see I'm holding these together. I'm hoping you can see there's a gap between the center poles of these cores, and that's to allow the core to store energy. Basically it will to a certain extent decouple the two windings, so they're not as closely coupled as they would be if this gap wasn't here. The bigger the gap, the more loosely coupled they are, and this gap allows the core to store energy in a more efficient way for a flyback type of switching system. If we go to the other forward converter type, then the core is different. In cross section it can be the same size, it can look very similar, but the difference is there is no gap. So it'll look more like that, so there's no gap at this point. And this again will be an example. I'll show you one. I've only got one of these in a second, but if we put the back edge of this, which is straight, hopefully you can see there is no gap between this and the two outer poles, a straight line. Whereas if we do the same thing with a gapped core, you can hopefully see that the center pole is shorter. So this is the sort of transformer we would use for a flyback type converter, and one like this is what we would use possibly for a forward converter type. Now of course we normally put the windings onto a former such as this, and then cores fit into that. Different shape of course for the E-type. So this is an EC type, this is an E-type, and you can see the difference is the center pole on the EC is round, whereas on the EE it's square. I prefer this type, it's easy to wind, but these work just as well. And of course these go in here, but there's one from each side. Okay, I said I'd tell you why I only have one of these. I ordered some of these for the project, got them off eBay, but once again fell foul of idiotic packaging. This is how they arrived. I didn't put them in this bag. There were 4 cores in here, all just dropped into a bag, and needless to say they arrived smashed to pieces. These are very brittle. If you knock 2 together they will probably just shatter, and you need to be careful, especially with the gapped type. So if you get ones with a gap, if you squeeze this too hard in the centre, you will break the outer legs off. So be very careful with these, don't bang them together, otherwise you will almost certainly end up with a bag of pieces like this. If you're going to ship them somewhere, wrap them separately. Don't be stupid enough to put them all in a bag like this. They will not get to the destination in one piece. So now we know what the core type is we want to select. We know what the topology is that we intend to use. We are going to design a flyback type switch mode supply. We'll start initially with this. This is probably larger than we need. This is an EE42, or more technically it's an EE42-21-15. So what numbers mean is it's 42 millimeters this way, it's 21 millimeters this way, and it's 15 millimeters that way. It's generally what those numbers mean. The EC is really the form factor for the transformer. Sorry, this is an EC. This is an EE. Okay, so now we know the type of transformer we want to use. So this particular one, it's actually bigger than we need. This will work on much bigger power output than the one we're going to design, but it'll be easy to use this initially to demonstrate the general design. I will be switching to a slightly smaller core later on, but for now we'll look at this one. Now this is an EE42, or more technically it's an EE42-21-15, and what those numbers mean is the EE is the form factor, the shape of the core and the way it sits on the board, so it's a horizontal layout. It's intended to be used like this, and it sits, as I say, horizontally on the board. You can get them that sit this way up with the pins in 2 rows at the bottom, and you can get other formats as well. And the numbers basically mean the 42 is this dimension, the 21 is this dimension, and the 15 is this dimension. So as I say, this is an EE42-21-15. The material for this particular core is PC40. It's quite an old material, and the modern materials are far more efficient, and you can use much smaller cores, but as I say, we're designing an old school supply here, so I thought old school material would make it far more in keeping with the feel of our project. But just bear in mind, if you use different material, you need to look at the data sheet, and we will look at the data sheet for the material in a future video when we start doing a bit of maths. I'll try and keep the maths as simple as possible. We'll need to dip into it now and again. But the next thing is, how does the switch mode converter actually work? So what we'll do is we'll just have a quick recap on the general idea for how a switch mode converter works, and in particular how the ferrite material is used within the transformer. Now, if you saw the series of videos I posted on the magnetic core memory, or if you read the book that I wrote in conjunction with that series, I explain in some detail how current in a winding on a core can change the flux in that core. So in short, if we take a core material and put a winding around it, copper winding, and then pass a current through that winding, if we put a step current, we make a step change in the current in the winding, then the current will start to increase, and the flux within the core will start to increase as well, up to the point where it reaches saturation. If we look at the current, then the current will also start to increase, but once the core saturates, the current will rise very rapidly, and this is something that you need to be very aware of when you design switch mode supplies. Now we're using a schematic or a design like this, so we've got a single-ended design, and that means that we're always going to be driving the flux in one direction. So when we switch on the current, the flux within the core will start to rise, and then when we turn the current off, the flux will start to decay. Now, one thing to bear in mind is it won't decay back to zero, so there will be some residual flux. But the amount of energy we can transfer is going to be the difference between the low flux level and the high flux level. I mentioned there are other topologies that you can use, and one of those is a bridge circuit, in which case it will drive the flux in both directions. So it will start by driving the flux in one direction, and then it will switch over and it will drive the flux in the other direction. The advantage in doing that is, of course, you can transfer far more energy for a given size core. We're not doing that, we're using single-ended, so we do need to take into account any residual flux. The other thing you have to be very careful of is to make sure that the way that you're driving the core and the way your circuit works is properly turning the driver device on and off, and also allowing the flux to decay as much as you can, because once the core saturates, as the flux has gone as high as it can, the current will very rapidly rise. So if you get a situation where you start driving the flux up, and then at the end of that cycle it comes down, but it doesn't come down far enough, and then the next cycle it comes up, doesn't come down far enough. If you're not very careful, you end up with a situation where the amount of energy the core can store is that, but of course if you're not going down to zero, the amount of energy the core can store drops with each cycle till it gets to the point where as soon as the device turns on, so when this device is switched on, if the core is already saturated, the current will immediately go very high and it will destroy this device. To a certain extent that can come down to the type of core you're using. So if you're trying to design a flyback supply and you don't have a suitable core, in other words you don't have a core that's capable of storing energy, you can end up with a very high current as soon as you switch the power on. Also bear in mind that you might be driving this at tens or hundreds of kilohertz, which means that this situation can arise very quickly, and it can appear that your driver device will fail almost instantly when you apply power. So this is one of the reasons that designing switch mode supplies can be a bit tricky. And what we will be looking at as we go through the design is we'll be introducing a few circuit elements that are there purely to make sure that the switching of our device is done in a way that's going to allow it to properly drive our selected transformer. You also of course need to make sure the transformer is wound correctly, and there are specific ways to wind switch mode supplies. It might seem a bit odd when we start looking into that, but if they're not wound, you don't wind the entire primary in one go, for example, you wind it in two separate parts, but we'll come back to that when we start looking at the transformer design itself. So that's the basic design we're going to take. The next thing we'll look at in the next video is how to start designing the actual transformer we want for our supply. Why we're selecting a core like this and the size of the core. How do you size a core for something like this? Now, having said that, I'm going to use a core that's much bigger than we need, and we can still look at the general maths for the core, and that will allow us to determine how many turns we're going to need on this. I showed you a formula in the previous video, but that only really applies to full bridge switching supplies. We need to use a slightly different formula for what we'll be designing, and we'll look at that in the next video.